Another characteristic of a linear graph is its y-intercept. This is the point where the curve crosses the y-axis. Since it is a point on the y-axis, it will have whatever units the y-axis has, and so will, in general, have a physical interpretation. For example, in the previously discussed position versus time graph, the line crosses the axis at some y value when the x value, in this case, is equal to 0. Since you have a position at time, t equals 0 seconds, the intercept would represent the position of the object being studied at the time the clock was started, that is, at time t equals 0 seconds. The y-intercept is shown by the arrow. It is the location of the graph where the x-axis, or time, is 0, and the y-axis represents, in this case, a starting position. Again, you must always look at the units to interpret the meaning of the y-intercept. Check your understanding of linear graphs by examining the graph and answering the questions. Now consider the following graph and answer the questions pertaining to curves E and F. Take a few minutes and review this video. Take some time to watch these videos. Quadratic relationships are those in which the dependent variable, that on the vertical axis, varies as the square of the independent variable, that on the horizontal axis. In its simplest form, a quadratic relationship can be expressed as y equals k times x squared, where k is a constant. In general, a quadratic relationship is one described by the expression y equals a plus bx plus cx squared. As an exercise in working with quadratic graphs, complete the table for the quadratic equation y equals 2x squared. Plot a graph of y versus x, then a second graph of y versus x squared. In the section on linear graphs, you saw that one way of getting information from a graph was to take the slope of the line. It is also possible to take the slope of any general curve at a specific point. The general definition of slope, as defined in the section on linear graphs, still applies, but the application is more involved. The slope of the curve at a point is found by constructing a tangent to the curve at the specified point. A tangent is a straight line that touches the curve at only one point. Use a ruler and move it until it touches the curve at only one point, the point that you are interested in knowing the slope at. Draw a straight line, then find the slope of this line. The slope of that line will be the slope of the curve at the point where the tangent line touches the curve. As an example, suppose that as a car races to town, data on its time and distance are recorded. The data is plotted on the graph shown here. We want to find the speed of the car at t equals 3 seconds, which will be given by the slope of the curve at the point t equals 3 seconds. We find the tangent line and take the slope. In some physical situations, the area under the curve is an important physical quantity. In the graph, the area under the curve between t equals 1.0 seconds and t equals 3.0 seconds is shown by the shaded area. The area can be determined by counting the squares on graph paper or by the use of geometry. For the area shown, the shaded area is the combination of a rectangle of width 2 seconds and a height 1 meter per second, and a right triangle of base 2 seconds and height 2 meters per second. Using this information and the formulas for the areas of a rectangle and a triangle, the area under the curve between t equals 1 second and t equals 3 seconds can be determined. Practice finding the slope of a curve by using a tangent line by estimating the slope of the curve in the following graph at points A, B, and C, which is the graph of an object's velocity as a function of time. Be careful to get the sign of the slope correct. What is the physical meaning of the area under the curve between t equals 1 second and t equals 3 seconds for this graph? Remember that it is important to look at the units on the graph. Hence, if you multiply the y-axis unit meters per second times the x-axis unit or seconds, and the results are just m for meters. This is a distance or length measurement. You can conclude that for a velocity versus time graph, the area under the curve will give you a length measurement. Just check the units when you do this, and you can see what the meaning of the area under any general curve will give you. Remember, area is one dimension. The y-axis times the other dimension, the x-axis value. As you have seen in the previous examples, when physical quantities are graphed, there is generally also physical meaning associated with such things as the slope of a curve or the area under the curve. To be able to obtain meaningful information from a graph, such things as the units of the quantities measured must be known. In addition, since graphs are representations of real physical situations, it is important to know when looking at a graph what the physical situation is. To address this important factor, a set of criteria have been developed to follow when creating scientific graphs. When the particular application or the physical data being represented may alter these criteria for the professional scientist, the following guidelines should be closely followed by students in the teaching laboratory. When choosing scales for the axes of a graph, choose scales that will cause the graph to fill the area of the page designated for the graph. If you are using a computer graphing utility, this will usually occur automatically. However, if the computer does not choose an appropriate scale, you should manually adjust the scaling on the graph until the graph fills the allotted space. The physical data plotted on a graph will, in general, have units associated with it. Both axes should be labeled showing the quantity being plotted, its units, and the symbol used to represent that quantity. For example, if you were plotting velocity on one axis, you might label that axis with velocity v m/s. If you are using a computer graphing program, this information must be typed into the computer. The graph should have an appropriate title that is indicative of the physical situation being represented by the graph. For example, if you were graphing data collected for a falling golf ball, you might title the graph Motion of a golf ball in free fall. Do not title your graph Y versus T or position versus time. This information can be obtained by looking at the axis labels. Such titles are commonly the default titles for computer graphing programs, but they say nothing about the actual physical situation being represented. Change the title to something descriptive. Other information that should be included in the title block of a hand-drawn graph include the name of the experiment, the date the data was collected, your name, your partner's names, and any other information that might be relevant. If you are creating a computer-generated graph, this additional information should be typed into the text box of the graph. The best fit curve should be indicated. This can be done with a ruler for linear graphs or with a French curve or flexible curve for other graphs. If the graph is linear, the slope should be indicated along with its units. If you are using a computer graphing utility, the best fit equation for the curve should be displayed. Many graphing programs do not display the units for the terms in the best fit equation. If yours does not, you should write in the units by hand or type them into the text box. Much of the power of science has been derived from treating complex systems in the simplest possible way. To do this, one usually tries to hold all the properties of the system constant. Then one property is systematically changed and another property is observed. After careful observation and measurement, scientists use graphs to look for the quantitative relationships between variables of a system and mathematics to communicate their results. Being able to draw the relationship between two variables at a straight line is a powerful analytical tool. By determining the slope and the starting value, an exact quantitative expression, a mathematical equation, relating the two variables may be written. But for this expression to be valid, the data used to generate it must also be valid. The following guidelines will help to obtain the best possible results from an experiment. Manipulate only one variable at a time in an experiment. If other variables are to be investigated, each should be looked at separately with all other variables held constant. Collect data over the widest possible range of the manipulated variable. If you think a linear graph is appropriate, draw the best fit to your data as a smooth line, not a segmented line. In other words, do not play dot to dot with the data points. If a linear graph does not seem appropriate, try various functions of the independent variable to see if a linear graph can be generated. Alternately, use a curve fitting routine in a computer graphing program. If your graph is linear, use the best fit line, not the data points, to determine the slope and intercept values. The idea of a best fit line is very important. The best fit line is the mathematical best fit to all the data points. Any measurement, no matter how carefully taken, has some inherent error in it, which could be the result of the equipment or bias on the part of the observer. When the best fit line is determined, the effects of the individual errors in the measurements are averaged out. This may mean that few, if any, of the actual measured points lie right on the best fit line. In the graph shown, the best fit line to the set of data points is indicated. Notice that the line does not actually pass through any of the points. The closer the line comes to the passing through the points, the more certain we can be that the best fit linear equation actually represents the experimental evidence. The equation that describes the best fit line is found by using the slope-intercept form of the equation of a line, y equals mx plus b, where y is the dependent variable, x is the independent variable, m is the slope, and b is the y-intercept. When calculating the slope, the best result will be obtained by using points where the best fit line crosses grid points on the graph and by using points as widely separated as possible. This process is illustrated by using the graph from the examples shown. Hopefully you can now take data and determine if the relationship between the variables is linear or a parabolic or quadratic relationship. Again, you can go to your textbook or teacher and ask for some example problems that will help you in this newly understood graphing process.